So over the years, I've encountered a number of people who've had a lot of new sorts of theories, cosmological models, physical models, models that replace relativity, various sorts of interesting ideas, and I'm not sure what to do with them. Often they say that they're right and Einstein is wrong, or something like that, you know, that sort of category. I started preparing this talk literally 40 years ago when I was an undergraduate and I was taking my initial physics classes. And I remember learning about Newtonian physics. And in Newtonian physics, we learned that force equals mass times acceleration. So if you push something, it moves. We know that. Then I learned a completely different formulation for the same sort of thing, and that is Hamilton's principle, which is behind Lagrangian dynamics. And that says that a system follows a path in which the difference between the kinetic energy and the potential energy is minimized. It's called the principle of least action. And both of these approaches give you exactly the same answer. And so this was mind-blowing. There's a way of looking at the universe where there's a principle, and there's a way of looking at the universe where there's a process. Very interesting. Also, other Newtonian laws, or things that evolved from Newtonian laws, can be matched with conservation laws. So we've got the conservation of energy and the conservation of momentum. Again, a principle, conservation versus a process. So the world seems to be divided, so far, into principle and process. Let's keep going. In optics, we learn Fermat's principle. So Fermat's principle says that light takes the path of least time. So if we're looking at a fish in a pond, the path that the light takes makes a bend because light travels faster through air than through the higher index medium of the water. And so we can tell the path that way. But there's another way of looking at it, and that's through Snell's law, which tells us that at the shift of index of refraction, there's going to be a bend and so on and so on. And this is, you can base this on phase matching conditions and so on. So again, there's sort of this principle, and then there's a process. Let's see, is there more? Before I do, actually, which one do you feel better with? How many of you prefer looking at the general principle in order to understand something? And how many of you prefer looking at the process, examples, to understand something? Okay, we're almost evenly divided. Okay, let's take a look at thermodynamics. And I've got 3 examples from thermodynamics. One involves how a system evolves in time. And we know from the second law of thermodynamics that the entropy must be maximized. So a system moves to a position where the number of options that that system has is maximized. There's another way of looking at that, and that is through the microscopic interactions. If you put a bag into hot water, a tea bag, the particles diffuse out, and you can look through particle by particle what happens, and eventually the tea gets distributed fully, and the entropy is maximized. Principle, process. A second thermodynamics concept. Let's take a look at a system at rest. So we know that if we have, for example, a reactant and a product, that eventually they equalize, they stabilize. And so at that point, you can say the system is at equilibrium. What's constant? The temperature, the pressure, the chemical equilibrium. We can also look at this from a different point of view, and that is an active process. This was initially developed by Einstein, among others. And that says that each process is dynamically balanced by its inverse. In other words, there's constant motion from the product to the reactant and back and forth. Both of these describe the same thing, principle, process. Third thermodynamics example, heat from friction. We know that if we rub one stick against another, that the kinetic energy that we've put into the sticks is going to eventually end up as heat energy. And so there's a conservation of energy. We can balance that by another view, and that is looking at the microscopic interactions. When you rub one stick against another, one molecule causes another molecule to vibrate, the vibrations produce heat, and so on. Electromagnetics. So we know that current produces a magnetic field. Maxwell observed electromagnetic interactions for a long time and very carefully codified them into a long series of equations, which were eventually reduced to Maxwell's 4 equations. One of these is Amperes Law, which I've shown here, and in particular I've boxed the equation that says the curl of the magnetic field, B, is equal to something that's related to the current. So what this is saying is that if you pass current through a wire, it produces a magnetic field, and the picture shows that. If you've got 2 wires in which you're passing current through them, those magnetic fields interact and the wires can either attract or repel each other. Let's take a look at another way of looking at this, and that is electrostatics and special relativity. So if you take a look at just a wire in the top picture here, you can see that we've got electrons in the wire, in the metal, and they're balanced by the ionic cores, which are the positive charges, and so everything's neutral. But we also know from special relativity that when things move, they tend to contract. That's Lorentz contraction, or they appear to contract from a stationary observer. And so if you look at this wire while the electrons are moving, it appears that the electrons are in higher density because the electrons and the space between them has contracted. And so the wire becomes not electrically neutral if you're looking at it the right way. Then if you have another wire that's adjacent to it that's also passing a current, those 2 wires will appear to each other to be non-neutral, and so there can either be repulsion or contraction due to special relativity. This was a particularly interesting one for me, and I went to a fellow in my department who's an electromagnetics theorist, really a brilliant guy. And I was talking to him about how you can derive magnetism, which is not one of the 4 basic forces, how you can derive it from relativity. And he was very puzzled. And I said, well, where do you think magnetism comes from? And he said, from Maxwell's equations. And I said, but relativity explains it. And he said, no, relativity comes from Maxwell's equations also. I was flabbergasted, but that really is another legitimate view. So we have the principal view and the process view. Let's take a look again. This one's a little more subtle, and I'll go through it. It's really for specialists. But we know that semiconductors have electrons that can exist at various levels. They can exist in what's called a conduction band, they can exist in a valence band, and they cannot exist in the forbidden gap. And silicon is an example of this. All the electronics that we work on is based upon the fact that there's a forbidden gap in energy. So where does that come from? Well, as a student, I learned that there's actually a periodic potential in a material. And so you can view the red dots as being the ionic cores, and you can simplify that with the green line, saying that there's sort of a step function periodic potential. And so when the electron is traveling through the semiconductor, it has a certain wavelength associated with it. When that wavelength is such that it keeps on hitting these barrier walls, the electron says, I'm fed up, I'm not going to move, and it reflects. Therefore, that electron is encountering the forbidden gap. If the electron has more energy, shorter wavelength, or less energy, longer wavelength, it doesn't encounter this periodic potential in the same way. And so from the periodic potential, we can derive a band gap. It's sort of a Fourier transform approach. Then I learned another thing in solid-state physics. And this is a complicated diagram, so bear with me. Let's just start on the right-hand side. So this shows energy, and it's an atom. And we know that an atom has electronic orbitals, the red line, the blue line, the orange line. And these orbital energies for the electron are discrete. Now, take the atoms and start smushing them together. As you squeeze them together, they encounter the Pauli exclusion principle, which says that you cannot have anything in exactly the same state at the same place at the same time. So the electrons cannot all be in the same energy. So what do? They spread out. And so the energies of the electrons spread out as you move the atoms closer and closer together. The vertical dashed line shows the interatomic spacing of the atoms in a solid. And so at that spacing, what do you end up with? You end up with bands, a gap, and bands. And so we end up with the same thing. This was mind-blowing to me as a student. Two totally different ways of deriving semiconductor band structure. Now, which one is process and which one is principle? So let's step back a little bit and take a look. So I just divided things into process and principle, but it's really a lot deeper than that. Principle can be a conservation concept. Process might be kinetics. Principle can be a purpose, the purpose of least action. The process might be the mechanism. You push this, it moves. It might be what happens versus how it happens. Principle tends to be more abstract, process tends to be more concrete. Principle tends to be a global thing, process tends to be local. And so in looking at the semiconductor example, the periodic potential is global, the spreading of atomic orbitals is local. And so therefore, that's how I would divide these two concepts. Then we want to go a little bit farther, and that's why I call this whole thing dualism. So we know the philosophical concept of dualism, which divides the world into mind and body, or mind and matter. And there's a real parallel here. Because I've got very little time, I won't go into that much. But so in semiconductor band structure, we also have principle and process. So let's take a look at another one. And this is the really tricky one, microscopic interactions. So we know that microscopic interactions are described by quantum mechanics. Quantum mechanics, one of the operational equations for quantum mechanics is the Schrodinger equation. Here I show an example of the time-dependent Schrodinger equation. How does this work? Well, let's say that we have here the example that's always brought up, the example of the double slits. So you're sending electrons one at a time through double slits. The electron goes through one slit or another slit. You know the story. It keeps on going, and you would expect that if you're sending particles through slits, you'd end up with just sort of a smear pattern on the target. But you don't get a smear pattern. Instead, you get a series of lines that says that the electrons, these particles, have wave-like characteristics which cause interference patterns from waves. So we've got waves, we've got particles. Very, very disturbing. But yet, quantum mechanics tells us what happens, it doesn't tell us why. Let's take a look at another example, and there are many, many. Let's take a look at black holes. So we know that there's an event horizon in black holes, and if anything encounters the event horizon and particles, radiation, everything falls into the black hole, never to come out again. Except for Hawking radiation. So Hawking figured out that there is a way to radiate particles from a black hole, and this has to do with pair creation. So in the vacuum, you're constantly creating particle-antiparticle pairs. They're created and they recombine. And if you have this pair creation occur near the event horizon, and the antiparticle, say a positron, falls into the black hole, and the particle comes out of the black hole, eventually the antiparticle will recombine with another particle inside the black hole and disappear, and you've ended up with a particle outside. Great, so that works. So you actually can radiate from a black hole in that way. So when I heard about this, I was really puzzled. Why doesn't the other process occur? Why don't you have the antiparticle falling into the black hole, the particle coming out of the black hole, sorry, the opposite way. Why don't you have the particle falling into the black hole, the antiparticle coming out, in which case, ultimately what you've done is you've just fed the black hole with more particles. You haven't had radiation. And statistically, you'd think there'd be an equal number of antiparticles going in and particles going in. So I went to my uncle, who's a well-known cosmologist, and I said, Uncle Werner, why does it happen this way? And he said, well, you see, Garret, you cannot have an antiparticle in free space has a negative total energy, the sum of the kinetic energy and the potential energy. And you cannot have an antiparticle in free space. And I said, why not? And he said, well, relativistic quantum mechanics says you cannot have an antiparticle in free space. Is that an answer? Well, that's what we're told. And that is the answer. And so again, once again, quantum mechanics tells us what, it doesn't tell us how. So therefore, if we want to make our principle versus process, we have quantum mechanics as the principle. What the devil is the process? So there have been a number of theories that have been proposed. One that I particularly like is stochastic electrodynamics. And stochastic electrodynamics says that the world is actually classical with the addition of zero-point fields. So zero-point fields are all over the place, and they cause a jiggling, and that jiggling is what we interpret as quantum behavior. And this was developed originally from some ideas by Einstein. It was developed over the years by Boyer and various other people. Just this last year, De La Peña, a professor in Mexico, published an amazing treatise called The Emerging Quantum. And what he did is he used stochastic electrodynamic processes to derive quantum mechanics. He derived the Schrodinger equation. He derived a fully quantum mechanical explanation for things. This may be a process way of looking at what quantum mechanics gives us a principle way of looking at. Is stochastic electrodynamics right? Is quantum mechanics right? I don't think that's an appropriate question. So has the world come to the doorstep of De La Peña and Boyer and a number of other people before whom have developed stochastic electrodynamics? No, of course not. They've ignored it. Because quantum mechanics gives the right answer, so why do you need to go anywhere else? But yet, something is missing here. So if we go and we look now at the parallel theories, we've got a series of parallel theories where there's principle and process. Two ways of looking at the same phenomena in each case, and giving us the same answer. The one outlier that I've found is quantum mechanics, where there is no established process way of looking at it. One thing that I found interesting in looking at this is that Einstein has his name behind three of these, between detailed balance, special relativity, and also stochastic electrodynamics to some extent. So I think this tells us the way that Einstein liked to look at the world. So now I ask you, which suits you better? Do you prefer one way or the other? I tend to be a process guy, but some of the brilliant people I know are principle guys. So let's see. What do we get from this? So most physical phenomena can be described by two different approaches. One that I'm calling process, one that I'm calling principle. Sort of a dualistic approach. Quantum mechanics lacks an accepted theory describing the process. And from at least my way of understanding, this is the problem with quantum mechanics. This is what we need to balance what we understand in quantum mechanics. Then to answer the basic question of which is right, which theory is right, when someone comes up with a theory that explains what relativity explains and says, no, this shows that Einstein is wrong. No. Nature just is. How we describe it is up to us. But we often make the mistake of thinking that our descriptions are a reality. The descriptions are just a description. And so my answer to many questions about one view versus another is both. Thank you.
York?
I'd like to make a couple of quibbles or perhaps clarifications. For the sake of the non-physicists in the audience, I'd like to point out that you were consistently referring to antiparticles when what you really meant were negative energy virtual particles. In terms of the conventional matter-antimatter, a black hole will produce as many electrons as positrons.
You can tell I'm not a particle physicist. Thank you.
Another small quibble is that I think you've misrepresented Einstein's allegiance. He originally derived relativity from Maxwell's equations. In fact, his first thought experiment in the area was his realization that if you could somehow move with a ray of light at the same speed, you would see that its fields were not obeying Maxwell's equations.
Okay, so I've got a quibble with you on that one. The way that something historically evolved doesn't define the way that we have to look at it. And so very often we start from some specific and get a general, and later say the general gives us the specific.
I'd just like to quote quickly some words from a little-known Cambridge mathematician from many years ago, G. Spencer Brown, and he went a lot on the definitions of words. So explain. Explain. That is to lay out flat, as on a map or a diagram, and so miss the complexity of the reality or royalty of the world as it is.
Thank you.
Garret, in regards to your quantum mechanical dismissal of the double slit experiment, I would at least like to propose a little quibble as well, and that is when you analyze the double slit with single particles going through the slits, Paul Dirac, another famous physicist, a standard model hero, said a particle never interacts with another, it always interacts with itself. So if we look at the particle in terms of a wave packet extending past both slits, then we kind of at least understand the interference that's occurring. And of course, the collapse of the wave packet onto a single dot, looking like an interference pattern, seems to make a little more sense that way. Just a suggestion.
Tom, we don't disagree at all.
Oh, good.
I agree with you fully, and I don't want to deride quantum mechanics. It works, and various interpretations of quantum mechanics, such as the one you described, work. I'm not saying they're wrong. What I do want to say is that there's another way of looking at it.
Yeah, and I love SED as well, so conceptually I agree with you.
Yes, Garret. Could it be that the difficulty in forming a process model is that we're trying to do it in black and white, whereas quantum mechanics is really in color, so to speak? In other words, we're trying to use a classical mind type approach to describe something that is fundamentally not classical, that's quantum, like quantum information.
So that's a deep question. And I don't, obviously I'm not the person who knows the answer. I don't know if anybody does. But I wonder whether we have sort of warped the way that we think about reality to conform to the Copenhagen view or other views of quantum mechanics. And so we've gone way out on a limb to try to understand something very, very strange, when in fact we don't need to do that. We can understand it from a more simple process point of view that fits our intuition better. I don't know, but I wonder about that.
Thank you, Garret.
Thank you.